Discuss examples of complete metric spaces, and the first example we have shown is that the n coordinates of real numbers, that is a, or n coordinates of complex number is a complete metric space with respect to 2 metric d2. And then I have given as an exercise that d1 and d infinity are metric. So did you check that kn is a complete with respect to d1 and d infinity? So try these problems which I am giving as an exercise. There will be some question in exams related to that. So just we have changed the metric. The space is same. Only metric we are changing. The proof is very similar. Even you can find it in books also. Any financial book. So next example is that continuous functions on a complex set, particularly closed interval AB is a complex set. So this is a vector space, and with respect to the sup norm or the max norm, because this is complex, the supremum is maximum. This is a complete metric space. So first we verified it is a norm, and that gives metric, and then every Cauchy sequence converges. Yeah, so this you try whether this is a you already verified this is a norm, but with respect to this norm or the corresponding metric. So what is the corresponding metric here? That is distance of f with g is norm of f minus g, and that is essentially the square root of integral a to b fx minus gx square dx. So with respect to this metric, whether this is a complete metric space or not. So it is easy to work with norm in this case, and you can you just take sequence of function like fnx equals to x power n, and try to see whether this converges to some functions or not with respect to this norm. And in fact you can take close interval a b to be 0 1. So try this exercise by considering close interval a b to be close interval 0 1 and the functions which we are taking x power n. So first question is whether this sequence is Cauchy, and second question is whether if it is Cauchy, then it converges to whether it is convergent or not with respect to this norm. So check and tell me in the next lecture what is the answer of this. So after that we discuss continuity in terms of uniformity. So uniform continuity is equivalent to the condition that in distance y, the distance of fun and fvn converges to 0 whenever un and vn are sequences whose distance converges to 0 in the usual metric. So we discuss proof of this result that whenever we have a complex set and we have a continuous function over complex set is always uniformly continuous. proof we already discussed. I think this is the same result, right? Yeah. Okay, so today we are starting some new topic, that is uniform convergence of functions. So I guess that you must have studied this also in analysis 1, but let us quickly revise this. So if we have a continuous function, sequence of continuous functions, that means we have f1, f2, fn. So for each n, we are defining the function fn from metric space x to metric space y be a continuous function. And the thing is that why we need uniform convergence. So let us see one example. So if we consider x to be the closed interval 0 to 1, and we take y to be the real line with the usual metric. So for every natural number, we are defining these functions. Define fn be the function from x to r defined by. So we are defining this function. Let us call it capital Fn function. So Fn we define our x to be n times x if our x lies in the closed interval 0 to 1 by n, and we take the value of the function to be 1 if x is in the closed interval 0 1 but outside this set. So that means it is in the open closed interval 1 by n to 1. And another function we are considering, that is fx. Fx is also the function from x to r, and it is defined as the value of the function is 0 at x equals to 0, and other where the value is 1. So when 0 close 1, the value of the function is 1. So what is the graph of this fn? Let us try to draw it. So for example, if we take n is equals to 2, what we get, f2x is 2 times x if x belongs to closed interval 0 to half, right, using this definition. And it takes value 1 if x is in the interval 1 by 2 to 1. Okay, so let us draw this function. And yeah, so similarly for n is equals to 3, we get f3x, which will be px if x is in 0 to 1 by 3, and the value is 1 if x is in the 1 by 3 to 1. Let us try to draw these two functions on the real line in the xy plane. So graph, to draw the graph, uh, yeah, so the value is between 0 to 1, right? And here also the closed interval is up to 0 to 1 over which the function is defined. So half will come here, 1 by 3 is somewhere here. So let us draw these two functions. The first function is f2, which is a equation of line, and the end point is, so 0 to half. So at 0 the value of 2x is 0, at half the value of 2x is 1. So at half value of 2x is 1. Right, so it is a line joining these 2 points in the closed interval 0 to half, and then on the other points in the closed interval 0 1 the value of the function is 1. Right, so up to here. So what is this? This is f2x. Similarly, if you draw f3x, then it is 3x up to 0 to 1 by 3. So at 1 by 3 it takes value 1, and then it takes value 1 on the other interval. Alright, so this is the function f3x. So now you can easily see the way we have drawn the graph. f4 will be from 0 to 1 by 4, right? And in that way. So as n approaches to infinity, we can see that the graph is actually approaching to the function fx equals to constant 1, right? So that is exactly this function. Fx is 1 for other than 0 value, and at 0 it is 0. Yeah, so it is easy to see from the graph that the function fnx approaches to fx for every x in the closed interval 0 1. So at each point it approaches to fx. So for example, x equals to half, you can see the value of the both function is 1 for every I. For x equals to 1 by 3, f3 onwards the value is 1. Right, so in that way. So this kind of convergence is known as pointwise convergence. Of functions, and here note that the function f is not continuous. So pointwise convergence does not imply the uniform the continuity. Right, so each fn is continuous from the graph itself, but its limiting function fx is not continuous on the closed interval 0 1. So pointwise continuity is not enough to ensure the continuity of the limit function. So therefore we are using the notion of uniform convergence. So let us define what do we mean by uniform convergence. So each fn is a function from x to y. X and y are matrix spaces, and in that case we say that fn converges to function f. So here f is also from x to y. So fn converges to f uniformly. So the definition of uniform convergence is that for every epsilon greater than 0, there exists a fixed natural number such that in the y metric fnx converges to fx for every n greater than equals to n naught. Note that here this holds for every x in capital X. Right? We have not mentioned that, but for all x in X. So this n naught does not change if we change x, but in pointwise convergence it changes. So that is the difference. between uniform convergence and pointwise convergence. So let us discuss a proposition. If we have two matrix spaces x and y, and if we have sequence of continuous functions. So Fn is a sequence of continuous functions which converges uniformly to capital F function. Then this function f from x to y is also continuous. So this is true for all metric spaces x and y, right? So proof is very simple and it uses the epsilon by 3 technique. So this technique is famous as the epsilon by 3 technique. So in which we divide the given epsilon into three parts: epsilon by 3, epsilon by 3, epsilon by 3, and then we use triangular inequality three times. So the sum of 3 epsilon by 3 is epsilon. So let us start with the definition of uniform continuity. So since Fn is a sequence of functions which approaches to f uniformly, what we get is for every epsilon greater than 0, there exists a integral number such that whenever we have fx with fn naught x is less than epsilon by 3, so instead of taking epsilon, we are taking epsilon by 3 for every n greater than equals to n naught. So whatever we are taking uniformly will take. So let us take n greater than equals to n naught. So this is true for all natural number bigger than or equals to n naught. So this is true. So in particular, this is true for n naught itself. And on the other hand, the function is each function is continuous. So if you fix any point, so since our function corresponding to this number n naught, that is f n naught, is a continuous function, by the so what is fn? Fn is a sequence of continuous functions on x, right? So at each point of x it is continuous, and since it is continuous, we can use epsilon delta definition. So for every epsilon, so epsilon we already take arbitrary. So using that epsilon, we get a delta corresponding to that epsilon. Using this continuity, we get a delta greater than 0, such that the distance of fn naught x with fn naught x naught is less than. So again, we are taking epsilon by 3. So this is true whenever the distance of x with x naught is less than delta. So whenever distance of x with x naught less than delta, we have distance of fn naught x with fn naught x naught is less than epsilon, right? But here we are choosing delta for the epsilon by 3, not epsilon. So therefore we are getting on the right side epsilon by 3. Okay, so these two estimates we got, and now using these two estimates, we will show that we get continuous. The limit function f is continuous, right? So what we use first that the uniform convergence, fn converges to f. In the second step, we used fn naught is continuous at x naught, right? So using these two, we will see that for every x in x, whenever distance of x with x naught is less than delta, what we want to show that distance of fx with fx naught, right? We want to show that capital F function is continuous at x naught. So to show that, we need to show this is less than epsilon. To show this is less than epsilon, we'll divide this using triangular inequality into three parts. So this is distance of fx with f n naught x, right, plus distance of f n naught x with fx naught, right? So we use triangular inequality first time. Now we'll use it again. So we get fx with n naught x plus fn naught x with fn naught x naught plus distance of fn naught x naught with f x naught. Right. So in the second step, we use triangular inequality for last term. So that divided into this plus this. That is less than equal to that this plus this. Yeah. So now we are done, because now we know that the first inequality gives fx with fn naught x is less than epsilon by 3 for every x, right? So in particular for x naught also, this is less than epsilon by 3. So that will give us this is less than epsilon by 3, and this is also epsilon by 3, less than epsilon by 3. So this gives epsilon by 3 plus, and what is this? This is just continuity of fn naught. So we use fn naught x distance with fn naught x naught is less than epsilon by 3. So this term is also less than epsilon by 3, right? So we get 3 epsilon. So that is epsilon. So what did we use? We use first that distance of fx with fn naught x naught is less than epsilon by 3, right? Similarly for this one. This is true for every n including n naught. So therefore we are using 2 times. And the other term is also epsilon by 3 using continuity of fn naught. So we are done with this proof, and that gives that whenever we have a limit function f which is the limit of continuous function and limit is uniformly, then the limit function is continuous. But in previous example, limit function is not continuous, and therefore using this proposition we get that fn does not converge to f uniformly, right? Because if fn converges to f uniformly, the limit function f must be continuous. So the next topic today we want to discuss is related to norm, that is known as seminorm. So seminorm theory is very important in to prove the Hahn-Banach extension theorem. So that we'll see later, but as of now, let us see what is the definition of seminorm. So if we have a vector space over set of real numbers or complex number, and on which we are defining, we know that on vector space we can define norm. Similarly, we are defining seminorm. So a map. So norm is also map from X to R. Seminorm is also map from X to R. Is a seminorm on X if it satisfies two properties. So norm has three properties. Here we are taking two properties of that. First property is triangular inequality. Second property is that norm of kx is equals to modulus k times norm x. So that property is this one. Right. So yeah. So first remark is that if we assume a given function p on x to r, it satisfies these two properties, then some of the properties we can derive using this property. The first remark is that if p is a seminorm, on x, then we know that p of 0, right? So we have this property. So in which if we take k is 0, if k is 0, then 0 into x is 0, right? And that we can write as modulus of 0 times p of x. Right, because if k is any number, then p of kx is modulus k times px. So here 0 times the vector x. If we apply p using the second property of seminorm, we get this. And then we know that if so modulus of 0 is 0 and 0 times px is a real number because p is a map from x to r. So 0 times real number is always 0. Right. So what we got is we got a certain information about seminorm that if p is a seminorm which satisfies second property and first property, then p of 0 is always 0. Right. So this is similar to that norm of x is norm of 0 vector is 0. Right. What this we are getting for the seminorm coming from the seminorm definition. And the second property is that if we use this, then we will get 0 is equals to p0 by 0, p0 by 2, because p of 0 is 0, and p of 0 we can write as x minus x for any vector x, right? Because x minus x is a 0 vector. So what is this 0? This 0 is not usual 0, it is a 0 vector. Because p is a function from x to r and x is a vector space. So that vector space always has 0 vector. zero vector we can write as a x minus x for any vector x. That is what we use in this step. And then we know that the first property gives that if we have two vectors x and y, then we can use the triangle inequality. So that will give us is less than equals to 1 by 2 times p of x plus p of minus x, right? Because this is x plus minus x. And yeah, so there should be bracket here. And then we can apply the second property. So whatever constant is there, we can take out as a modulus sign. So if you apply that, we get this equals to 1 by 2 px plus modulus of minus 1 times px. And modulus of minus 1 is 1. So that is px plus px. And that is nothing but p of x. So this is true for every x in x, that p of x is always greater than equals to 0. Right, so let us write down finally what we got. P of x is always non-negative for all x. So this property is related to, if we compare with norm, this property is norm of every element is non-negative. Right. So if we compare now the seminorm properties with norm properties, then seminorm satisfies all the properties of norm except the converse of this. So here we prove p of 0 vector is 0, but converse is not true. That means p of x is 0 means implies x equals to 0 vector. Right. So let us take that as a remark C. So if the seminorm P satisfies the condition P of x is equals to 0 implies x equals to 0, then P is called a norm. Right, so norm we don't write by px, we usually write by norm x. Right, so in this sense, every norm satisfies all the properties of seminorm, but every seminorm does not satisfy this particular property of norm. So that means seminorm is a generalization of norm. Right, so for example, if this is a norm on x, then p of x defined to be this is a seminorm. So every norm is a seminorm, but converse is not true. Converse is true only when P satisfies the property C. Okay, so we have already noted that a vector space on which we have defined norm is called the norm-linear space. A norm is given is called a norm-linear space. So every time we'll not write norm-linear space. Whenever we say norm space, that means it is a vector space along with norm. So so this is a new direction. So from here onwards, we are starting with norm and properties of norm. So if you recall, we have noted that every norm induces a distance where distance is defined as norm of x minus y, right? If you have any two vectors of nonlinear space and if you have a norm, you can define corresponding metric. Every norm gives a metric, and moreover, we'll get norm satisfy many properties of the modulus, right? Because modulus itself is a norm over the set of real numbers, right? So note that if you take any vector norm of x, then we can write it as norm of x minus y plus y, and then we can use triangle inequality, right? So what we get is norm of x minus y is less than equals to norm of x minus y. So now if we switch x and y, we get norm of y minus x. So combining these two equations, we get modulus of norm x minus norm y is less than equals to norm of x minus y. Yeah, so how this inequality will be used? So this inequality is very useful. So if you know if xn converges to if xn is a sequence in x which converges to x, then xn minus x in norm is less than epsilon, and that will give us right. So for every epsilon greater than 0, there exists and not belongs to n. So this property holds if xn converges to x. That means xn converges to x, and that will imply norm of xn converges to norm x. So using xn converges to x, if we know this inequality, we can prove norm of xn converges to norm x. So this we already used for the sequences in real numbers and complex number, but this is true in general for the matrix spaces. Any sequence in matrix spaces, we get whenever xn converges to x, norm of xn always converges to x. So other property also we get. So here what we proved is, so therefore we proved that norm is a continuous function. So what do we mean by norm is a continuous? Any function is continuous if xn converges to x, f of xn converges to f of x, and f is norm here. So that means xn converges to x implies f of xn converges to f of x, that is norm xn converges to norm x. So therefore, norm is a continuous function from x to r. So that is first observation. The next observation is that you can also prove that the x is a non-linear space. So we have two operations over x, addition and scalar multiplication. So question is that addition and scalar multiplication are continuous or not? Answer is that yes, addition and scalar multiplication are also continuous. So note that. So addition is continuous. How to show? To show addition is continuous, we need to show that xn converges to x, yn converges to y. Then we need to show xn plus yn converges to x plus y. Right? So let us try to prove that. If we want to show xn plus yn converges to x plus y, we need to take the difference between them. Right? So we know that this difference using trigonal inequality, it is less than equals to norm of xn minus x plus norm of yn minus y. Right? So if this holds, then xn converges to x, yn converges to y, implies xn plus yn converges to x plus y. Right? So that means f of xn yn converges to f of xy, where what is the function? Function is x plus y. So in this sense, addition is continuous. So here actually we are taking the function f, which is two variable function. Right, so basically we are taking x cross x kind of thing. So R2 in the sense of R2. So product metric kind of thing we are using here. And the last thing is scalar multiplication. So on the other hand, we know that if xn converges to x, and if we have any scalar, then norm of kxn minus kx, which is nothing but modulus k times norm of xn minus x, and this gives kxn converges to kx. So therefore the scalar product in x is continuous function. So basically addition and scalar multiplication is continuous. That is, we already know in terms of convergence of sequence that if xn converges to x, then 2 times xn converges to 2x is exactly that property. 4k is equals to 2. But here we are considering it as a vector space operation. They are continuous. Okay, and then if we know that we have a norm, then we have already defined the open ball. So that is uxr, open ball about x of radius r, that is y belongs to x, such that norm of x minus y is less than r. Right, so this is the open ball about x, of radius r. So we want to show that if we have any point, yeah. So another notation we define is closed ball. So closed ball means u closure of xr. U closure of xr is all the points such that norm of x minus y is less than or equals to r. In the above ball, we are taking only those y such that norm of x minus y is less than r. But in the second that we are taking norm of x minus y less than or equals to r. So if you want to show that this is closed set, so in that case, we need to show that every point uh, so if you can show that if the points whose norm is equals to r is the limit of this set, right? So let us try to prove that. So suppose y belongs to x such that its norm, its distance from x is exactly r, right? So y is a point such that its distance from x is exactly r. Then we can find elements yn defined by y plus 1 by n sequence of x minus y, right? So now if n approaches to infinity, this part will be 0. So that means this sequence converges to y as n tends to infinity. So yn converges to y as n tends to infinity. Let's see what is norm of yn, the distance of yn with x. So note that distance of yn with x is basically norm of y plus 1 by x, x minus y minus x. So if we write this in terms of y minus x, then this is essentially 1 minus 1 by n y minus x, right? By taking y and x terms separately, we can verify that these two are equal, and then this is nothing but modulus of 1 minus 1 by n. So since n is greater than equals to 1, right, for large n, yeah, so let us write for, yeah, so in any case, so this times norm of y minus x, and norm of y minus x is r, right? That is our assumption. Norm of x minus y is r. So we got this, and that is less than or equals to, strictly less than r. Even if n is 1, this term is 0, and if n is greater than 1, it is less than r. If it is 0, then also it is less than r. So what does this gives? This gives yn is an element of the open ball. So what we proved is if we take y on the kind of boundary of the ball, then we can find a sequence yn in the interior, right? So that will give us the set what we define is a closed set. So basically every point is a kind of limit point, and all limit points will be anyway inside that set. So that is used here. So therefore it is a closed set. Okay. So let us stop today at this point. If you have any doubt, you can ask now.